Hi everyone, today we will discuss electrostatics. So let us start with the definition of the charge. So here if you consider this electric charge, so electric charge always occurs as some integral multiple of some fundamental unit of charge. Means electric charge always occurs as some integral multiple of, if you consider the electronic charge E, suppose charge on every electron and that is represented as a small e, so the charge value, it is always some integral multiple of this e, and that is also termed as charge is quantized. Means when we consider the integral multiple of e, so here we can say charge q, it is equal to some integer, suppose n into this e, so q is equal to n into e. So here you can consider this q is equal to n into e. Either you can take this capital N or small n, that is your choice, and that is an integer. So charge is integral multiple of this e, where e stands for electronic charge, charge on every electron, which is equal to 1.6 into 10 to the power minus 19 Coulomb. Unit of charge, it is Coulomb, and charge on each electron, it is 1.6 into 10 to the power minus 19 Coulomb. So whenever we consider charge on certain thing, so it will always be some integral multiple of 1.6 into 10 to the power minus 19 Coulomb. Suppose twice of this, thrice of this, 5 of this, 6 times of this, and so on. So that's why it is also termed as charge is quantized. It has been quantized. So, and in general we write it as q is equal to ne, or q is equal to n into this e, or electronic charge n into e, where n is your integer, either capital N or small n. Now, as far as nature of the charge is concerned, charge can be positive, charge can be negative. Another feature of charge is total charge always remain conserved. So it means summation of charge, if you consider summation of charge, so it is always conserved, it is always constant. Like in nature there are certain things which are always conserved or which are always constant. Mass is always conserved, and the total mass never get destroyed. So total mass always remain constant or always remain conserved. Similarly, the total energy always remain conserved, total charge always remain conserved, and there is another term also, so momentum is also conserved, but momentum is conserved only when summation of all external force acting on the system, it is 0. But as far as charge, energy and mass is conserved, they are always conserved without any exception. In case of momentum we have an exception, the summation of force, it should always remain, summation of force, it should always be equal to 0, or the resultant of all the forces acting on the system, if it is 0, then only the momentum remains conserved. But in case of charge, mass as well as the energy, it always remains conserved. So these are the certain features. Charge is quantized, charge always remain conserved. Okay, charge is can be positive, it can be negative in nature depending on the number of electrons and all that. Corresponding to these features, we have Coulomb's law. Coulomb's law states that there will be force of attraction between the two non-similar charges. If one is positive, another is negative, and they are placed in the electric field of each other, then there will be force of attraction. Similarly, if one is positive, another is also positive, or one is negative, another is also negative, means similar charges, plus plus or minus minus, then there will be force of repulsion. So if one is positive, suppose plus q, and another is negative, suppose minus of q, so there will be force of attraction. So this will try to attract this one, and this will try to attract this one. Similarly, if there are repulsion, and suppose q negative and q also negative, so this charge will try to repel this side, and this will charge to repel this side. Similarly, positive and plus plus, so in that case also we will have force of repulsion, and here we will have force of attraction. As far as the force of repulsion or attraction is concerned, it can be represented like this between the two charges. Suppose you have this charge q1 and we have this charge q2. One is with the positive sign, another with the minus sign. So obviously there will be force of attraction. So here, if you consider this line between them, then this charge is attracting this and this charge is attracting this. So you will get this relation. this sign represent, this arrow, that this charge is attracting this, and this represent that this charge is attracting this. So both are attracting, or they are attracting them mutually. So there is mutual force of attraction. If you consider these two charges, suppose Q1 as well as Q2, and both are either positive in sign or both are either negative in sign, means the similar nature, then there will be force of repulsion. So that is again represented outside the charge. This is represented within the charge, just to avoid any confusion whether we are representing force of attraction or force of repulsion, just to get that clarity, because once we start solving problem, there will be many charges, there will be mutual force of attraction as well as repulsion simultaneously in that particular question, just to have a clarity as far as the direction, because force is a vector quantity, so always you will need the direction, in which direction those forces of attraction or repulsion are acting. So just to have a clarity of the diagram, we must represent it properly, otherwise unnecessarily we will get some mistakes. So here plus plus or minus minus, so we will represent like this. Okay, in various books you can find various representation. We are not concerned or bothered about it. We will follow up our own system, not our own, but that is the accepted system. So here, so this charge is being repelled by this charge, and this charge is being repelled by this. That's why we have this direction as well as this direction. So suppose here it is Q1, here it is Q2. So this way we will try to represent the force of attraction or force of repulsion to avoid any confusion. Now let us see what will be the magnitude of the force of attraction or repulsion. So that magnitude, it is given by this Coulomb's law. This states that whenever two charges will be there in an electric field, there will be force of attraction or repulsion which is proportional to the product of the charges. So forces between the charges, it will be proportional to product of the charges. So suppose here you have this Q1 and we have this Q2. So they are placed at a separation or at a distance of this R. Okay, when we say this distance R, so if you consider this point charges and dimensionless, if we assume, then this R is distance between this point to this point. But if you consider spherical charges, suppose having certain dimension, then this separation between the charges, it is considered from center to center, this center as well as this center. So this is R. Okay, from here we will consider this R. Separation between the two centers of the two spherical charges means if they have any dimension, then it is R is taken from center to center. If it is point charge, then R is obviously distance between those 2 points. So this force of attraction or repulsion, it is proportional to this product of the two charges, and it is inversely proportional to the distance between them. Inversely proportional to the square of the distance between them, yani 1 upon R square. So F proportional to 1 upon R square, F proportional to Q1, Q2. So this is the rule, and that we get from Coulomb, that is Coulomb's law. So proportional to product of the two charges, inversely proportional to distance square. So F proportional to 1 upon R square, F proportional to Q1, Q2. Now if you combine these two statements, so we get F proportional to Q1 Q2 upon R square. Just combining these two statements of this law, we get F proportional to Q1 Q2 upon R square. Now this proportionality, it will be replaced by a constant, and that we get F is equal to some constant, suppose K, Q1 Q2 upon R square. F is equal to some, this proportionality is replaced by a constant, that is K. So F is equal to K Q1 Q2 upon R square. So that you can see here, Q1 Q2 upon R square. Now this K, it depends on the nature of the electric field, whether it is free space, whether it is vacuum, whether it is medium. So we have different value of this K. So let us see this relation. So this diagram you can see here, what that we have drawn. We have this, suppose, charge Q1, we have this Q2, separation between them it is R. Now force experienced by 1 by 2, that you can see, force experienced by 1 by 2. So we have this F of 1, 2, and that is this direction, provided they are similar charges. If you would have taken non-similar charges, then it will be, direction will be different. Then in that case we will represent it like this, in between the two charges. Similarly, force experienced by 2, and this charge by 1, so it is in this direction, again force of that repulsion. So that way we represent R is the separation between the two charges. If it is spherical, it will be center to center distance. Now this K is replaced as 1 upon 4 pi epsilon naught. The value of this K, it is 1 upon 4 pi epsilon naught. This is termed as your electrostatic constant. Yani two charges are traced, they are experiencing some force of attraction or repulsion. That force is equal to some constant K, Q1, Q2 upon R square. That K is termed as electrostatic constant, which is equal to 1 upon 4 pi epsilon naught, where epsilon naught is known as the permittivity of the free space or the vacuum. It means the charges are lying in the free space or vacuum, and if there is no other medium, then the permittivity of that medium, it is considered as epsilon naught. It is read as epsilon naught. So it is 1 upon 4 pi epsilon naught Q1 Q2 upon R square. Value of 1 upon 4 pi epsilon naught is 9 into 10 to the power 9 Newton per meter square, Newton meter square per Coulomb square. 9 into 10 to the power 9 Newton meter square per Coulomb square, that is in MKS system. Now these things you may keep in mind, you may not keep in, because these values are generally provided in the question paper. So from here you get F is equal to, replacing K by 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught Q1 Q2 upon R square. Now in case of, if there is some medium, let us say not the free space, not the vacuum, if there is medium, then this epsilon naught, it will be replaced by epsilon, this simply epsilon, which is termed as the permittivity of the medium. Either you say absolute permittivity of the medium, or simply we say permittivity of the medium. So absolute permittivity of the medium or permittivity of the medium. Now there is the free space and there is some medium. So it means there will be some relative permittivity. So epsilon R, it is represented as the relative permittivity of the medium relative to free space. Yani the permittivity of some medium with respect to its free space or the vacuum. So relative permittivity of the medium relative to free space. So it is equal to your epsilon upon epsilon naught, means epsilon R, it is equal to epsilon upon epsilon naught. Okay. So from here you can consider epsilon is equal to epsilon R into epsilon naught. That is permittivity of the medium, it is equal to the relative permittivity into the permittivity of the free space or the vacuum. So epsilon is equal to epsilon R into epsilon naught, or we can say epsilon R is equal to epsilon, means epsilon upon epsilon naught. That means what? Permittivity of the medium with respect to this free space or vacuum. So that way we can calculate the relative permittivity. So 1 upon 4 pi epsilon Q1 Q2 upon R square. Now if you elaborate it, so can you say that F, it is equal to 1 upon 4 pi epsilon, and that epsilon is equal to how much? Epsilon naught, epsilon R Q1 Q2 upon R square. So this becomes the general expression. Depending on free space or vacuum, this epsilon naught, it will be epsilon R, it will be equal to 1, and in that case you get 1 upon 4 pi epsilon naught Q1 Q2 upon R square, means this relation. I hope this is clear. Now as force, it is a vector quantity, so now we can represent the same expression in terms of vector. So here you can see this F vector, F21 means force experienced by 2 by 1, by the charge 1. When the charge 1 is applying some force on 2, either it is attracting or it is repelling depending on the nature of the charges. So F21, that will be 1 upon 4 pi epsilon naught q1 q2 upon r square. Now here we have this unit vector r. That unit vector r, all of you are aware of this when we put this unit vector r or n in general somewhere with the vector. So this represents the direction. So this r here, unit vector, this r only represent the direction, that in which direction this force F of 21 that will act, means force applied on 2 by 1. So what will be the direction of this? Otherwise this represents the magnitude of the force, 1 upon 4 pi epsilon naught q1 q2 upon r square in free space or vacuum. If it is some medium, then it will be 1 upon 4 pi epsilon q1 q2 upon r square. So same thing you can see here. So F21 is the force experienced by Q2 due to Q1. Similarly F of 1, 2, that will be our force experienced by 1 by 2. F of 2, 1 or F of 1, 2. Force experienced by 2 due to 1, and this is force experienced by 1 due to 2. That is the only nomenclature that we use and these symbols for that. Now Coulomb's law applies actually only to the point charges or charge particles. So this law is in this form, F is equal to q1 q2 upon r square k q1 q2 upon r. That is applicable directly in case of point charges. It's clear, either the point charges or charge particle, if you have some charge particle or some point charges. Now you can suppose have a rod, charge is uniformly distributed throughout. In that case we will have the same kind of relation, but directly we can't use this relation F is equal to k q1 q2 upon r square. When we apply, we will have certain modification in that, and then again we will come back to the same relation. So that will be termed as uniformly distributed charges, whether it is a sphere, solid sphere, uniformly distributed. You have a rod, there will be uniformly distributed charge. So how to calculate force experienced by the charges, so that we will discuss when we start solving problems. So this law is applicable for the point charges or simply charge particles in this form. It is applicable everywhere, but directly not in the form that we have discussed, that is F is equal to k q1 q2 upon r square. Now consider this electric field. So when you consider this electric field, what is this electric field? Now just to understand this, suppose you consider a charge q in this region. Okay, now if force of attraction or repulsion is observed by another charge, okay, at this point, this point, this point, this point, and so on, suppose in this region, then we say that the field or the region of this charge is up to here, this surrounded place, because depending on its magnitude, okay, it generates electric lines of forces. We will just discuss what is the electric lines of forces. So it generates the electric lines of forces, and the region up to which we feel the effect of that electric lines of forces, that is only termed as the electric field of that charge q. So here we have this charge q. Electric lines of forces are generated in all possible directions. Suppose there is some test charge. When we say this test charge, so this test charge is always unit positive charge. Unit positive charge is termed as the test charge. Now when we say unit positive charge, it means the nature of that charge is positive and magnitude of that charge is 1. So unit positive charge, okay, magnitude is 1, nature is positive. So that is termed as the test charge or unit positive charge. Now suppose you place a unit positive charge somewhere here. If this charge experiences some force of attraction or repulsion, it means its electric field is up to here. Similarly, if you consider you place this unit positive charge here, and if it experiences force of attraction repulsion here, it means its region is up to here. Similarly here, here, here. It means if a unit positive, the region up to which a unit positive charge experiences a force of attraction or repulsion, then that region is termed as the electric field of the charge. So here if you consider this charge q, then the electric field region of this charge will be up to this. Now suppose if I put a charge, unit positive charge here, and if it is neither repelled nor experienced, if it does not feel any experience, it means the unit this charge is not having the electric field up to here, it is only up to here. So it means now we can summarize this discussion and we can define this electric field as a region of space in which electric charge experiences a force. Electric charge, that means the unit positive charge, is known as electric field. A region up to which a unit positive charge experiences the force of attraction or the force of repulsion, that is termed as the electric field. The force per unit charge, means force experienced by unit positive charge, experienced by a very small test charge. When we say very small test charge, means that is unit positive charge at a point in an electric field is called the intensity of the electric field of that point. How much intensity is, what is the strength of that, that will be measured by this electric field intensity, that is also termed as electric field strength. So if you have suppose electric field intensity, okay, so what will be the electric field intensity? So that can be considered as F by Q. Suppose force experienced by unit positive charge. So force experienced by unit positive charge, if you consider, so F is equal to how much? In general, Q1 Q2 upon R square, some constant K. Now if you consider this is in MKS, if you consider CGS, or in case of this charges, okay, in case of this electrostatics, we have the unit ESU. Instead of CGS, we have the unit ESU, electrostatic unit. ESU means electrostatic unit. So in case of mechanics or other chapters, we can use MKS system or we can use CGS system. But in case of electricity, we use either the MKS system, that is SI, as well as we use this ESU, electrostatic unit. In case of ESU, whatever be the medium, whether it is free space vacuum, whether it is any other medium, value of this K, it is 1. In case of MKS, it is K is equal to 1 upon 4 pi epsilon. Epsilon, it is again replaced by epsilon naught epsilon r, so that becomes your 1 upon 4 pi epsilon naught epsilon r. These are the different statistics. Now here, if we consider the ESU just for our understanding and simple calculation or simple analysis, then this can be considered as Q1 Q2 upon R square. Just we are trying to ignore 1 upon 4 pi epsilon just for lengthy calculation, because it is having its own value. So for understanding, if you consider that the system is measured in terms of ESU here, then K it is equal to 1, so F is equal to Q1 Q2 upon R square. Out of these two charges, let us say one is the test charge. So one is test charge, so if Q2 is suppose unit positive charge, when we say unit positive charge, in that case F it is equal to Q upon R square. Taking this, Q1 is equal to simply Q. So F is equal to Q upon R square. This is the force experienced by unit positive charge, which defines the electric field due to this region. Means the electric lines of forces or the electric field spread due to this charge Q, because this force is experienced by what? Unit positive charge. Who has spread that force? This charge Q. Who has experienced that force? That unit positive charge. So now again the same thing, it can be defined as force experienced by unit positive charge. It is defined as the electric field strength or the intensity, because this is the strength or this is the force generated by this Q. So the electric field strength or electric intensity of this charge Q, it will be Q upon R square. That is termed as electric field strength or electric field intensity. So here if you define this, so force experienced by unit positive charge, if it is equal to E, then force experienced by Q amount of charge, it will be equal to how much? F is equal to Q into this E. Force experienced by unit positive charge, if it is equal to E, then force experienced by Q amount of charge, it will be equal to Q into E. So that's why we have F is equal to Q into E. E is the intensity, simply intensity or electric field intensity or electric field strength. Force is the between the two charges placed at some distances, or either in case of your ESU system or in case of MKS system. So depending on that we have these relations. So F is equal to Q into E. So now you can understand this. Force on a unit positive charge, this clear. Then E is equal to limit Q tends to 0 F upon Q. When we say Q tends to 0, so this Q becomes what? Q is tending to 1, that is unit positive, very small charge. So E is equal to F upon Q. So E is equal to, from this can you say it is F upon Q. So that's what we have here. So intensity or electric field strength, that is F upon Q. I hope this is clear. So if you want, we can again summarize this, because these are some of the important things. F is equal to Q1 Q2 upon R square in case of ESU, or you can simply put K in general. So K Q1 Q2 upon R square. Force experienced by unit positive charge, that becomes your F is equal to KQ upon R square, taking Q1 is equal to Q, Q2 is equal to unit positive charge, that is 1, so F is equal to KQ upon R square. This force experienced by unit positive charge is termed as intensity. So this becomes your intensity. Force experienced by unit positive charge, that is termed as intensity. So intensity is also a force. So force is a vector quantity. So this intensity is also a vector quantity. This clear? Now, so for unit positive charge, force experienced is how much? E. So for Q amount of charge, force experienced, it will be how much? Let us say it is F dash. This F dash I am writing so that I can distinguish that this F dash is different from this F. So F is equal to Q into this E. For unit positive charge, force experience is E. For Q amount of charge, force experience, it will be Q into E. So that is the relation between the force, intensity as well as the charge. I hope now it is clear. Now consider these lines of forces. The lines of forces, suppose you have a positive charge Q. Okay, now as far as we have just discussed the electric field region, so it means it will have its own electric field region up to which a force of attraction or force of repulsion is experienced by a test charge. So now these electric field lines, or as far as the definition of the region is concerned, it will spread or it will have electric lines of forces in all possible directions. So this will have electric lines of forces in all possible directions. So it will originate from any charge, any positive charge. Okay, so it originates from the unit positive charge and it terminates at the at the negative charge. It originates from the positive charge and it terminates at the negative charge. So here you can see it is originating. These electric lines of forces are originating and it can go up to infinity. Depending on the magnitude of the charge, it depends on how far it will be, it depends on the magnitude of the charge. So how strong its electric field is, depending on the magnitude of the charge, we feel those electric shocks. This clear? An electric shock means if we are within this region of these electric lines of forces, so we will face an electric shock due to the presence of this charge Q, because it has these possible electric lines of forces which can act on us, and because of that we can have some kind of electrical process going on in our body. So here, so depending on magnitude of the charge, it can go up to any extent, like up to infinity. That is theoretical or hypothetical you can say, but it goes up to infinity. Another property is these electric lines of forces never intersect. They are curved in nature and they never intersect. One, it has spread, so it will go in all possible directions, but these electric lines of forces, they will not intersect at each other. Only they are intersecting at what? The point of origin, and that point of origin is the charge, presence of the charge at that particular point. So here if you consider lines of force in electric field is a curve. It is always curved such that the tangent at any point on it gives the direction of the resultant electric field. Obviously If you have a curved line, then to calculate the direction, we always draw the tangent. So here, if you consider this, then if you want to find what is the direction of that field, electric field line, so draw a tangent, and that tangent gives you the direction of the electric field along this curved line. If you are moving, it is not a case only for the electric field, it is case for everything. If you are moving along this path, curved path, then what is the direction of your motion? At this particular point, this is the direction of your motion, tangent at this point. Similarly, if you draw a tangent here, then direction of your motion is tangent at this point, tangent at this point, because you are moving along a curve. So at every point you have the different direction, and that direction is defined by tangent at that particular point where we need to measure the direction. Same is the case here with the electric field line. The direction of the electric field line, here it is tangent to this point, here it is tangent to this point, here it will be tangent to this point, and so on. Here it is tangent to, if you consider this, tangent to this point, and so on. That is the general nature as far as the curved motion is concerned, or any other system is concerned. So that's what this statement says. Direction of the resultant electric field strength at that point. Field lines originate on positive charge. The origination starts from the positive charge, and it terminates at the negative charge. Originate on positive charge and terminate on negative charge. Field lines never intersect. That's what we have discussed. They are not intersecting any other, and they behave as if they were tendency for the lines to repel one another, means they will diversify from each other, they will not converge, they will diverge but not converge. Okay, the electric intensity at a point is the number of lines. If theoretically or experimentally, if you want to calculate what will be the value of the electric field, then if we can calculate the number of lines, then that number of lines give the value of the electric field. As we are calculating F by Q is equal to E, or F by Q is equal to E, or F is equal to QE. With that relation, we calculate the value of electric field strength or electric field intensity. But by counting the number of lines, we can calculate the electric field strength. Number of lines of force streaming through per unit area, normal to the electric direction of the intensity at that point. Per unit area, normal to that. Okay, the per unit area normal to the surface, that is also termed as area vector. So these things we will discuss when we start discussing the Gauss theorem, the electric flux and all that, because there we will have to analyze the concept of the area vector and all that. Okay. So here you can see this. This is the positive charge. Electric lines of forces, they are originating from this. Similar here also it is positive, so it is this is negative, so it is terminating at this. It is coming from the positive side and it is terminating, gets terminated at the, if there are two charges, one negative, one positive, okay, and this is negative, so it will originate, it will terminate here, it will originate, it will terminate here. That's what it has been shown here. It is originating and it is terminating, originating, it is terminating, and so on. That's why we have this bound surface here. Otherwise, if there is presence of only this positive charge, it will spread in all possible direction, it will go up to infinity or a larger distance. In general, you can say infinity, it is just a theoretical or hypothetical situation. So we will discuss in the next class.